Welcome to the course in General Relativity. My name is Renato Renner. I'm professor for quantum information theory, but this semester I'm teaching something which is a bit more remote for me, namely General Relativity. It's actually not the first time I'm teaching this course. I did so 2 years ago. And so for me, this is now the second time. It's, of course, under slightly more difficult circumstances, but nevertheless, I'm very much looking forward to this semester, and I very much hope that you will enjoy this course. So before we start with the actually interesting things, I have a few organizational things to tell you. And maybe the first that you should know is that this course is a course that is offered jointly to ETH students, as well as to students from the University of Zurich. And also students from the University of Basel will attend this course this time. There are also a few others, a few guests from other places. Everyone is, of course, equally welcome to this course to attend both the lectures and the online tutorials. And there will also be in-person tutorials. Those are accessible to ETH students and university students. So, first of all, I would like to also introduce Giulia Mazzola today. She's one of the teaching assistants for this course. She will give one of the exercise lessons. She's also today here to moderate questions. So maybe I should already now encourage you very strongly to ask questions, at least as soon as we enter the actual material, the actual physics. So for me, it's rather difficult in this online scheme to get a feeling for how you actually get the material, whether you understand it or not. Usually I see that just in the faces when I stand in front of a real audience. And here I just see some names, and a few of you have their videos on, but that's quite rare usually. So I really need your feedback. And this feedback is actually most useful if it comes in terms of questions. Don't shy away from asking very simple questions. The experience is usually that many others are actually very thankful to have some colleagues who ask the simple questions and stop me if I'm too fast. You may ask questions either by using the raise hands button, that depending on whether you use a computer or an iPad or a tablet is maybe in a different place, but I'm sure you will find this out. You may also alternatively use the chat function and just write your question there, or just write there that you want to actually ask the question orally in case you don't find this button. Giulia will today overlook both the raise hands and the chat and notify me if anything comes up here. I mean, actually, she will not always be there. As on Thursday, we have someone else, but there will always be a moderator looking out for questions by you. Now, you may, when you ask a question, of course, you should unmute your microphone. You may also want to turn on your video. It's usually, for me, easier to answer a question if I see the reactions in your face, but you don't have to if you don't feel comfortable to do so. Okay, so then a few admin things that we need to clarify before we start. The first thing is the lectures, as you know, probably by now, are purely online. There are no in-presence lectures, and this will be for the whole semester. However, the tutorials will be offered as in-person tutorials. So you may come to ETH, to one of the exercise rooms, and see your colleagues and see the TA in real. I will just in a minute make a small poll to see how big the demand is. And then depending on that, we will organize more or less of these tutorials. There will in any case also be online tutorials, or at least one online tutorial, which will, like the lecture, be recorded. So you can always, so you can essentially do everything from home or from wherever you are. All the information, so in particular the links to the corresponding tutorials, the recordings, the Zoom addresses or Zoom room numbers will all be posted on the Moodle account. And maybe this is for me an opportunity to briefly share my screen, and because the screen here should show the address of the Moodle page for those, this is particularly for those who are not ETH students who could not log into to the corresponding pages on the My Study system, or on the, so this is the address. You may try this one, but you still need a Moodle account to access this page. Your university, whatever it is, should be able to provide you with such an account. And then to actually put you as a member of the course, you would need to be registered, and you can do this by writing an email to me or to Henrik Wilming. So Henrik Wilming is a senior TA who is responsible for the organization of this course. You will also find, by the way, his email address on Moodle or on our group webpage in case you haven't managed to log into Moodle. Okay, so yeah, about the recordings, usually it takes me some time to put the recordings online. They need to be rendered, and this takes several hours, but I will always try to make the recordings available on the same day before midnight, I hope. And so you can watch, if you miss the course, certainly on the next day. Now we need to make the first short survey, and maybe I'll briefly stop again the screen share. So first of all, I think you all have a yes, no button somewhere. Please make sure you can identify that, because you will need to press that now a few times. So my first question will be, who of you is interested, or are you interested in in-person tutorials? So press yes if you would like to come to ETH to an actual tutorial where you are here on campus, as opposite to having just an online, participate in an online thing. So if you're interested in such a tutorial, press yes. If not, press no. So now I see that we have roughly 150 participants, but far less answers. So I'll wait for a few seconds until people found their buttons, and we'll probably see how to proceed. Okay, so it looks to me that there is certainly a demand for in-person tutorials. There are at the moment 63 yes votes for that. Okay, so the next thing is to determine when they should be. There are actually 3 slots foreseen for that. And I guess there are also some things in the chat. So I guess Julia can notify me if there's anything important there. But the next thing we should do is to determine suitable times. So we may also, by the way, be able to offer a separate tutorial for university students of the University of Zurich on the campus of the University of Zurich. So maybe that's my next question. If you are now a university student of the University of Zurich and are interested in attending an in-person tutorial, press yes. And if you are a university student but would just go for an online one, press no. And if you're not a University of Zurich student, do nothing. Then we can see whether there is a need for a special tutorial on that side. So maybe you should now somehow reset your earlier vote so that it's no longer there. Yes, maybe there was, so you should clear your previous reaction so that we have a new clean poll here. Okay, so now I cleared it now. Okay, you cleared it. So yes, please press again, just that we have a clear answer now. Okay, so there's clear. Then I need to determine whether or not, okay, we will see whether we will offer one. There is not a big demand in this direction. So then we reset the poll again. And there is a last thing I need to poll you, which is about the timings of the tutorials. So one possibility is to have, I write this here, on Thursdays from 4 to 6 in the evening. Who would like to attend that one? Please press yes now. You don't need to press no otherwise. Just press yes if you're interested in that one. Wait for 10 seconds and then we will do the other option. So Julia, you take the numbers, I guess. Yes. Okay, so then let's do the next. So if you're interested in the Friday option from 2 to 4, please press now yes. Okay, good. And if you're interested in the last option, which is from Friday from 4 to 6, press yes now. Okay, thank you. So there's some remaining information. One is that the start of the tutorials will be next week. This week are no tutorial lessons. The exercise and solutions will be distributed on Moodle. So please make sure you have access to Moodle until next week. You may also hand in your solutions, but you would need to do that via scan. So I would encourage you, because we will provide the solutions, that you actually essentially correct your exercises yourself. You check, you compare it with the solutions. I think this is also some process in which you can learn a lot. But if you still have remaining questions, for example, if you solved an exercise in a different way, then you're of course free to scan it and send it to one of the teaching assistants.
Renato, just a small question. One asked when the online tutorials would be. I guess it is set to Thursdays for now, but it should be variable depending on the demands of the students, right? The online tutorial.
Yeah, I mean, we can still shift it. So we will maybe have one if there is enough on Thursday afternoon, and then we can still query the students in that tutorial to see what the exact timing should be. But it will be roughly at that time, because we only have rooms there, so we are not arbitrarily flexible there. So it will probably not be shiftable by a large amount, just due to the inavailability of rooms, of large rooms. But by the way, the online there will anyway be an online tutorial on Thursday at between 4 and 6 that will be streamed. So this will anyway take place. Then on the Moodle, we will also put the forum. If you have questions about exercises or the lecture, you may ask the questions there, and the teaching assistants will answer them there. I already mentioned that Henrik Wilming is responsible for the organization. You can find his address on Moodle. And the lecture notes will also be made available on Moodle. I already put there the lecture notes from 2018. I will update them continuously during the semester and put updated versions there. There will not be big changes in the first part. There may be additional material in the last part, and I will come to that later. There is also literature recommendations there, but actually to follow the course, it's not necessary that you read anything else. The lecture notes and the course itself are supposed to be self-contained, but of course it's always interesting to read more if you, or to see more if you're interested or want to have a different perspective, so you find some recommendations there. There are also some related courses, and I just mentioned that because this often comes up. One is, of course, differential geometry, which is an important let's say, tool for or kind of mathematical device to do relativity. So you may want to attend a course in differential geometry, which is usually offered, for example, at ETH in the mathematics department, but this is not mandatory. I will also give you a self-contained introduction to the necessary concept of differential geometry. It will, of course, be very focused on what we need, so it will not be a course in differential geometry, but it just means you don't need, as a precondition for this course, have knowledge in differential geometry. The same is true for special relativity. In principle, everything we do will essentially build up general relativity, of which special relativity is a special case. Having said this, it's of course extremely useful for intuition to already know about special relativity, which was, for example, treated which is usually treated in electrodynamics courses here at ETH, sometimes also in classical mechanics courses. So you may want to look into that to update your knowledge, but again, this is not a precondition. maybe there are here and there certain things I mentioned about special relativity that are only understandable if you already know that, but it's not a precondition to understand the course, but it's highly recommended that you look into that a bit so that you're familiar with the way of thinking there. Okay, I think that's all about the organizational part. Are there any questions about that?
One small remark about the handing in of the exercise sheets.
Yes.
I think we didn't discuss this, but they're allowed to hand in sheets, and I guess it's when they get the sheet, then they have 1 week to solve it and then to hand
Yes.
in.
So I think if you want to kind of really hand in a full exercise solution, you should do that within 1 week from when it was handed out, because otherwise it will be difficult for the TAs to keep track of what's going on. But I would recommend, as I said, that you correct them yourself, and only for in special cases where you have solutions that you proposed and don't know whether they are correct, and you cannot find out whether they are correct from our provided solutions, maybe because we did it in a different way, then you can just maybe scan that part and ask the teaching assistant. So I would really recommend that you do it in a very focused way, and not just generally send the whole thing to the teaching assistants. Okay, then if there are no questions, you can start with the more fun part. So this was maybe a necessary part. You just make sure everyone is ready and has all the information required. But I guess there are no other questions. I hope there will be more questions when I start with the actual material. So what I'm going to do is to first give you an overview on the course. So today will essentially be a quite smooth or gentle introduction into the whole topic. So the course or the lecture today will probably not be very representative for what is going to follow in the rest of the semester. So if you are going to decide on whether you actually want to attend the lecture in the future, you should at least await the Thursday lecture, which will be much more technical than today, and will probably give you a better impression on what is going to expect you. But today, I think I just want to provide you with some general knowledge about what general relativity is. So I will in particular tell you where it is situated in the landscape of physics, of the different theories we have in physics. And then I will tell you a bit about the principles that it is based on, in particular the equivalence principle. I will also show you an example that illustrates how strong this principle is, or how powerful this principle is, and which also illustrates why this principle can actually be used to get quite far in the development of a theory. And then finally, I will already give you essentially the main essence of the theory, which are the Einstein field equations. I will write them down. Of course, you will not be able to probably fully understand them, maybe not even partially, but the idea is that this will allow us to essentially see the goal of where the lecture will go to. So to understand the Einstein's field equation is one of the central goals of the first part of this lecture. And so it's probably useful if you see that goal once from far, so to speak, and then we can approach it. And after half the semester, we will understand them in very much detail and know what these different symbols that occur there actually mean. Okay, so I will, in this lecture, use here my iPad to write. On the right-hand side, I will try to show you the same notes in a slightly smaller view, so that you see a bit backwards what I did in the previous page. I hope I don't forget to scroll there, and if not, then remind me of that. And of course, these notes will also be made available on Moodle after the lecture. Okay, so let's start. So I will start with, as I said, with an introduction. So the first chapter is really called Introduction to GR. The general theory of relativity, as you probably know very well, was developed by Albert Einstein, and it was essentially really one of the theories that was developed in, I mean, not in one go, but at the end it appeared as you know, at a very, very well-defined time in 1915. There were, of course, pieces available before, but essentially 1915 is the year of birth of this theory. And in contrast to other theories like quantum mechanics, which has pieces and that were put together in over years, relativity was just there as a fully developed theory, which also is maybe a sign that the theory is extremely nice, both from a conceptual and from a mathematical viewpoint, and quite well understood today, more than 100 years later. So where, as I said, I will start telling you where it is situated in the landscape of physics. And for this, I usually draw a diagram which those who attended earlier courses that I gave may have seen, because of course the other theories are also contained in this diagram. And this diagram will at the end have 3 axes. And these axes, I start with 2 of them, are related to constants of nature. Let's say the horizontal axis I could choose to be the velocity of light. More precisely, I write here 1 over the velocity of light. And what I mean by that is not that you can change the velocity of light and make it smaller or larger. Rather, what I mean is that when you look at a particular problem in physics, then you typically have certain typical velocities. For example, if I look out of my window and see a bike outside, then it has some velocity v. And now, of course, this velocity v is much smaller than c. So in other words, 1 over c is much smaller than, is much larger than 1 over c. And this means, if I'm talking about bikes running around, I'm essentially in this region here of the diagram. I'm in the region where comparably, where 1 over c is in a way quite small. Now, I mean, in this sense, we should always think of this. So what this means is compare it to other quantities. The same is true for the other axis, which I choose to be g, which is the gravitational constant. So what I mean by that is that if I'm here in this region, right down here, then I'm talking about problems where in a way the gravitational constant is compared to the things I'm looking at so small that it doesn't matter. So that's the way of thinking. So if, again, maybe it was unclear what I said before, if I'm here on this axis, then 1 over c is so small in this sense compared to 1 over v of the velocities I'm looking at that I don't need to care about it. And if I'm here, this means I'm looking at problems. For example, if I do an experiment in a lab here, then the gravitational force is usually not very relevant if I, for example, look at electromagnetism experiments. So in a way, G is compared to these typical forces very small. The gravitational coupling is very small compared to what they do. Of course, you may also think of a world in which you increase G and increase 1 over c, which would mean you actually make the velocity of light much smaller. That would be equivalent, because it would just mean if you increase 1 over c, you make the velocity of light at the end so small that it becomes relevant in our daily life. Suddenly a bike is almost as fast as the velocity of light, and then you would end up being here when we talk about bikes. But currently when we talk about bikes and experiments on Earth, we are somewhere here. And this is really the region where we essentially have, for example, classical mechanics. I just abbreviate that with CN. So this is where classical mechanics is situated. If you now go to the right in this diagram, then of course, as you may expect, now we are talking about velocities which are comparable to the speed of light. In other words, when we are in this world of large velocities, compared to them, light is no longer very fast. Or in other words, this thing here no longer holds, and this no longer holds, and this is when we have the special theory of relativity. So I could write here SRT. And of course, as you know, electrodynamics, which is mostly about radiation and light, or includes that at least, is also in a way situated in this region. Now, general relativity is really the part upstairs. So this is where we are now in this course. And maybe something to notice here is that general relativity is not only interesting. So this is the region when we have very large velocities and the gravitational effects are very relevant. But it's not only interesting here, it's also interesting, for example, here, or necessary here. So this is the region where we have still small velocities. An example are the movement of planets. The movement of planets is clearly here, because the movement of planets compared to that light is very fast. So 1 over c is in a way negligible compared to 1 over v for the velocity of a planet. So I'm here, I'm not in the regime of where SRT is relevant, but nevertheless I may have strong gravitational forces, because, for example, if I look at Mercury, a planet close to the Sun, the gravitational force is very relevant, so I'm somewhere here. So general relativity is really a theory that is already giving us interesting results beyond classical mechanics, even if I look at small velocities. It's unlike SRT in a way. And we will actually look at various things in this regime. So, for example, when we consider big stars or even black holes, we are often talking about this regime, although in the case of black holes, this is no longer maybe so well defined because it depends on the system of reference. But this is really where the general theory of relativity is situated. Now I said that there are 3 axes, and of course these 3 axes, the third one has to do with quantum mechanics. So I'll also put that into this picture. So I could essentially say that there is also an axis going in this third dimension where I write h bar. And actually, as a quantum information theorist, I shouldn't be happy about this third axis, because it's certainly not true that h bar is the only relevant thing. It's not true that in a world where h bar is in a way, or where the relevant quantities are very small compared to, or h bar in a way, or not comparable to h bar, I still have necessarily classical effects. But nevertheless, let's just understand that schematically. Then what I mean by this third axis is when we move to quantum theory. And then, of course, I have in this third dimension still the other axis. So there's still, essentially on the back of this diagram, I can make go to relativistic speeds, which means I go here to the right, and I can go into a regime where gravity becomes relevant. And then I can again draw or put the theories. And for example, if I ask what is here in this region that I indicate here, then I would say this is, for example, non-relativistic quantum mechanics. That's what you learn, for example, in quantum mechanics 1. Then if you go to the right, if you take into account velocities which compared to the speed of light are large, then you're here. So this would be essentially, for example, relativistic quantum field theory. So quantum field theory is a theory that can deal with the case where velocities are comparable to the speed of light. Now there is still, and of course, quantum electrodynamics would also be somewhere here in this region. Now the question is, of course, what is here on the top? So this top thing is really when we are both in quantum mechanics and we have gravity. So we went in this direction towards the quantum world, but at the same time we turned gravity on, if you like. And here, of course, as you may know, we don't yet have an established theory. So when people are talking about this, they often mention quantum gravity. Maybe I write this here, but this is not the theory we actually have as an established theory. So here we have a big question mark. And so in a way, general relativity goes in a different direction than quantum mechanics. And the big challenge is to find a theory where we can do both at the same time. And this challenge is one of the big research questions in theoretical physics. Many groups in fundamental physics are working on that. And as I said, so far, I don't think there is a convincing answer. So that's something for you to do once you have finished your physics studies. Okay, so that's first just to make clear to you where this whole theory is situated. Are there any questions about that? Because otherwise I would then actually continue with some more specific things about GR. Okay, so far probably everything was more or less clear, and indeed that's something that is very general and not specific to GR, but it's certainly good to know where or to be aware of how general or non-general GR is. So it's in a way a purely classical theory. And towards the end of the lecture, I will talk a bit about the challenges that arise when we try to go into this direction. But this will probably just be something for the last 1 or 2 weeks. Because many things there, or most things there, are still open. So there's not much I can tell you which is already established. So the next thing I want to talk about in this introductory part of the lecture is the equivalence principle. And the equivalence principle is, in some sense, a principle that doesn't allow us really to fully derive. So it's not that we just have this principle and can fully derive relativity from it, but the principle essentially is the basis for the introduction of most of the concepts we have in relativity. It really guides the way towards the Einstein equations. One needs some other assumptions, and maybe you could call them other principles to really arrive there, but it's something that is really maybe distinguishing the theory from other theories. And so maybe one thing one should know is what you have seen in the diagram that I showed you before, is that relativity or general relativity is essentially a theory of gravity, because it's really relevant when the gravitational constant is no longer negligible, which means gravity is not negligible in our considerations, if you do an experiment involving gravity. Now, you could say, therefore, general relativity is just compared to other theories like those we have here, introducing an additional force. And introducing an additional force should be quite easy. We just put the new force law. And that's essentially what Newton did. Newton proposed the force law. He said how, for example, 2 planets attract each other. And that would essentially allow us to go in this direction. However, what is different in general relativity, and this is really a fundamental difference from Newtonian theory, is that gravity is not introduced just by postulating a new force, essentially ad hoc, or even by experiment, supported by experiments. It's in a way much more fundamental. So rather than introducing just a new law that you see from experiments, you essentially go back to a principle and try to derive this new force law from this principle without the need to postulate an explicit formula. So what gravity theory or what general relativity really achieves is essentially to get Newton's force law in the special case. I mean, of course, it will be slightly modified, but to essentially get something that is equivalent to Newton's law in the regime that we usually have, let's say in our planetary system, except for Mercury, but you get it from a very general principle that is not just a postulated formula. So what is this principle? The equivalence principle actually exists in several versions. And one of the versions, and I'll start with that, is the weak equivalence principle, which is something that is already there in Newtonian mechanics. So let's start with that one. We have the weak equivalence principle. And here I really want to spend some time on that because this is really basic. You need to understand this very well in order to later really appreciate the concepts that arise from all that. So this is also called the Galilean equivalence. And as the name suggests, this is an old principle. And in the sense that it's already relevant to Newtonian, or it's already actually obeyed by Newtonian mechanics. So what is the principle? It's essentially stating, and you should have heard it already maybe in classical mechanics, that the trajectory of a point mass, so it talks about the trajectory of a point mass in a gravitational field. I write this really explicitly, depends only on the initial position and velocity. So you may now ask what else it could have depended. And indeed, the principle can be extended by saying what it doesn't depend on. Of course, the idea is already when I say only, it only depends really on that, but one can explicitly say what it doesn't depend on. So what is independent, to be very clear, of other physical properties that the point mass may have. So this principle is so important that it's certainly worth reading it more than once and thinking about what it really implies. So what are other properties that it could have? For example, it could, the point mass in reality is, of course, for example, a particle or a molecule, and maybe the trajectory could depend on the composition of that molecule or on the structure it has. But the equivalence principle says this is all irrelevant. The trajectory really only depends on the velocity and on the initial position. Of course, we know that this is true, and I just want to remind you, because we will build up from there. So the next few things I'm telling you are probably completely known to you already. Nevertheless, I will need them later, and therefore I'll write them down briefly, explicitly. So the first is that the statement that I already made, that Newtonian mechanics satisfies this principle.
Sorry, I have a question.
Yes?
You said that we weren't going to prove it from like a postulate, but this is a postulate, right?
Yes, this is a postulate, yes. Mm-hmm.
Okay. Okay.
Yeah, so this is not something we kind of derive. And so I think when I say principle, okay, there are, I'm sure philosophers actually make a distinction between what is a principle and what is a postulate. At the end, I think if you look at it from the viewpoint of physics, this principle is really not so precise that we can use it like an axiom in mathematics. So we somehow have to interpret it in the right way. It's more maybe a guiding principle, I would call it myself, because it tells us in which direction it should go. But they're all words which are sometimes actually not so clear how to interpret. And there have indeed been many discussions in the literature, and there are still ongoing discussions about what this principle really means. So it's actually very interesting to think about that. There's a whole research community still active in trying to understand what this principle means. And maybe just to say one word more about that, because this is a very, let's say, interesting point also today. I told you that today people are working on quantum gravity. And of course, now one approach is to go back to these principles and ask oneself, if you really take these principles serious, but interpret them in a quantum mechanical way, should we then not get automatically a theory of quantum gravity? Obviously, we don't have such a theory, so this approach hasn't worked, but that's one approach, to just take them as a guiding principle. But then, of course, if you go to quantum mechanics and it talks about the point mass that depends on the velocity and position, then you're already screwed, because in quantum mechanics, a particle doesn't have a well-defined initial position and velocity. So in this sense, this principle doesn't even make sense in quantum mechanics. So in that sense, it's not really something one would postulate as certain true because it doesn't even make sense in a way, but it could still be a guidance, because you could say, oh, maybe then it means an approximate position or an approximate measurable velocity and so on. But this is just to make clear you should be careful. So the bottom line is the principle in quantum mechanics is not even well defined. Nevertheless, as you will see today, it's extremely useful. Okay, so thanks a lot for the question. So Newtonian mechanics, as I said, obeys the principle. So this principle, therefore, cannot really go beyond Newtonian mechanics. So we cannot hope, I mean, if you already have a theory that obeys it, we cannot hope that we automatically get general relativity just by applying this principle. So what do I mean when I say that Newtonian mechanics obeys this principle? What I mean by that is that if you look at the force law from Newtonian mechanics, then this force law essentially tells us that the inertial mass times the acceleration, which I write here as a second derivative of the position of a particle. And if I underline something, I mean the three vectors, or the vector in three space. Later we'll of course talk about the four space, the four-dimensional space-time, has this form. And we also know in Newtonian mechanics, there is this law of gravity that I mentioned before, which was just introduced. I mean, I say it ad hoc, maybe it's not that ad hoc, but it's just something that is postulated as a formula. You may, by the way, derive it from Kepler's law, if you want, but at the end it's an explicit formula, and it's not, doesn't have the beauty of a principle in the sense that there's nothing that tells you why, for example, if I write this force law, there is now like power of 2 in this thing. Actually, when I write it like that, there's a power of 3 here. But the fact that the gravitational force decreases by 1 over square the distance is something that is just postulated, and it could also be 2.1 or something else. Of course, it would lead to different observational consequences, but nothing else would be wrong with that. And if you take these two things together, then you find, of course, I mean, I'll just combine them, that you may write an expression for the acceleration of the particle, which at the end will determine its trajectory. So the left-hand side is essentially the relevant thing, the relevant mathematical object that determines the trajectory. And if I insert what I've written above, then I could write this as m0. Now I should explain why I wrote here m0. So I deliberately made here a distinction between the mass that enters the force law, the Newtonian force law, and the mass that enters the gravitational law. There's a priori no reason to assume, and these are just proportionality constants, but there's no reason to assume they are the same, except that you can experimentally verify. If I had, for example, the force law from electrostatics, the Coulomb force, here, instead of m0, I would have the charge. And of course, the charge has nothing to do with the inertial mass. They're completely different quantities. But in gravity, it turns out that there is also a mass, and it turns out that if I write it like that, I get a ratio, and this ratio is constant. So let me first finish writing the expression. There's, of course, still this sum over j, and then I have here mj. So, and the scenario here would be, maybe I forgot to say that because this is the standard scenario, but let me again say, what this here tells me is what is the force on a particle with mass, gravitational mass m0, exerted by a number of other particles, which I number by j, with individual masses mj and positions xj. So that's what this thing tells us. Probably this was already clear to you, but that's what Newton told us. And if I insert this expression, or if I rewrite it in that way, you see that we have this fraction at the beginning of m0 divided by m, by m inertial. And this fraction I shouldn't say it's one. Of course, it's at the end one in our system of units, but it's just a constant. It doesn't depend on the structure or the composition of the particle. In that sense, it's a constant. And of course, this constant can be chosen in such a way that everything is absorbed by G, and this thing here is just one. But that's an experimental fact. So that's not something that follows from anything. We just have this as an experimental fact. However, if we took now this principle that I mentioned here, so if we take, so let's suppose you just had this thing here given, these two laws with an M inertial and an M0, which are a priori different, and then you wrote it in that way. And then you ask yourself, what does this principle, what does the weak equivalence principle tell us? Then the weak equivalence principle tells us that this side here, the trajectory, that's the acceleration. And of course, if I know the acceleration, I completely know the trajectory, that this trajectory should only depend on the initial position and velocity. So of course, if I integrate over the acceleration, these are just essentially the integration constants, the initial position and the velocity. So if I from this derive the trajectory, I need the initial position and the initial velocity, but this tells me the right-hand side should not depend on the structure of the molecule or the particle, which means that this thing has to be always the same. So the weak equivalence principle would be the reason to say that this has to be a constant, which I can set to 1. You see, the weak equivalence principle can in that sense also be tested, because we can now go to an experiment and measure this. These are these free fall experiments where we see whether this thing is equivalent to that one. And indeed, all experiments, and there have been very sophisticated ones, have confirmed that this is constant, which means that the weak equivalence principle has been to a very high precision confirmed so far. Okay, so now I think
Sorry?
yes.
So you're saying that it's not that like it follows mathematically from the formulation of Newtonian physics that the equivalence principle holds, but simply that like in our regular scale things we can test it experimentally and it holds.
Yes,
correct?
so you can take two positions. One is you can really take the experimental viewpoint and not care about principles. And then you just start with two different expressions here, like you would start in electrodynamics with one is charge and one is, I mean, this would be the charge and this would still be the inertial mass. And then you just find experimentally that this is always the same. And then you could say, oh, that's interesting that they are the same. Maybe there's a deeper reason behind it. Now, the other way to approach it is to say, maybe there are certain principles, so let's just try what these principles tell us. And one is this weak equivalence principle, which will tell us this has to be 1. And of course, if these two, I mean, they're just different viewpoints of the same. At the end, we have a theoretical justification why this should be 1, and the theoretical or conceptual justification would be the equivalence principle. And we have an experimental reason to say that this is one which is really the experiment which confirms this. And of course, the nice thing is that the two things are in agreement so far. So in other words, experiments, so all experiments to date don't contradict the weak equivalence principle. We can never verify a principle, but we could falsify it. So we could say the weak equivalence principle is a principle, a postulate that so far hasn't been falsified by experiments, which is actually very hard to find. You could say, oh, this doesn't mean much that it hasn't been falsified, but try to come up with a principle that is not easy to, that it says something non-trivial, but is not falsified. So you will not find many principles, and the weak equivalent principle is one of them. So in that sense, it's a very remarkable thing, although it's a very simple thing, and by now maybe very well understood in a way in the classical context. Okay, so we haven't now gotten very far so far, but so the interesting part will now follow. So the next thing I will now tell you what is the Einstein equivalence principle. And then from Einstein's equivalence principle, we will already be able to do something very interesting, namely to understand why rays of light are bent in gravitational fields. this can already be directly essentially understood from the principles themselves. Now, because when we have in-person lectures, we usually have breaks in between, I would also like to make a break of until 5 o'clock. The break means that I'm here to answer, let's say, questions as I would do that if I was in a lecture hall. So I just stay around, but I will not continue with the material. So you may also briefly get some fresh air until 5, and then I will restart. But you're, of course, more than welcome to ask questions in the meantime. So let's do that break, and we will then reconvene at 5. And you can just stay online. If you like, you can also log out and log in again. Okay, so are there questions you would like to ask me in the meantime?
I didn't fully understand the difference between the M0 and the M inertial. Could you just go through that again?
Yes, sure, yes. So here on this page, I have 2 different laws. And I mean, they're really 2 different things. One is the law which tells me that if I exert some force, which doesn't need to be, by the way, this is an F underlined. I hope it's visible that it's not an E, it's an F underlined. So it means if I apply some force to a particle, then I could ask the question, how fast does this particle accelerate? And so the force could, for example, be just a spring or something like that. And then, of course, we know that the stronger the force is, the larger is the acceleration, but there's a proportionality constant in between. And this proportionality constant is the mass of what we perceive as the mass. But we have only one expression of the mass, because in our description of nature, usually, we are already used to the fact that this M inertial that appears here and the M0 are the same. But think of it just, you detect this law. I mean, you don't know anything about physics, suppose, and you just notice when you apply a spring, let's say you have a spring which has which is calibrated in a way so that you know for a given length it exerts a certain given force. Now you take this spring and go to different bodies, and you just check how fast are these bodies accelerated when you apply the spring at the same length, and you measure it each time. And then you will find that for different bodies, the acceleration will be different. And there's, however, it's always proportional. So the larger the force, the larger the acceleration, but this proportionality factor depends on what you accelerate. If you go there and accelerate, for example, this glass of water that I have here, then it turns out this M is larger than if I do it with an empty glass, then this M is small. So I find this law here, this is just, first of all, a proportionality constant for this force law. Don't call it mass. Then let's say you do a completely different experiment. You find out that if you have 2 masses, I mean, you can for the moment even forget about the sun. Let's suppose we have just a mass or a body 1, and we have our thing which we call 0, our test particle, again this glass. So maybe I find out that this thing is attracted, for example, by a big mass like the Earth. So I measure how much force the Earth exerts on this thing, and I would measure that by, for example, countering with the spring and see like create a balance between the spring force and the gravitational force, and then I can read from the spring how much force Earth, which would be, for example, M1, executes on this glass. And then I also find that if I have a filled glass, then this proportionality factor that occurs in this law, this is now a completely different law, it has to do with gravity, is larger than if I have an empty glass. So this is a different, a constant that appears in a different law. So this is just the law that relates acceleration to force. And this thing has nothing to do with acceleration, it just relates force to, it quantifies force that comes from a gravitational source, which would be another mass. But in both cases, we have some proportionality factor that depends on what I apply it to. And now, in that sense, they're really very different things. They're just two different laws with two different proportionality factors. Now, it happens that in our common language, we call both of them mass. So the way the mass that I measure if I stand on a scale and measure my weight is usually kind of that one and that one here. But I could also, the mass that I feel when I, for example, I ride my bike and try to start very hard after when the red light turns to green, then I need more force the larger this thing is. And this is also, I would also say it's my mass that makes this hard to start accelerating after a red signal. Now, the point is, of course, both of these laws talk about the force, so I can kind of combine them into one, and then I get this thing. And now we can say, okay, now we have this quotient appearing. So if I'm only interested in the acceleration and I get the force out of the game, I'm just interested in the acceleration executed by gravitational force, then because I use these two laws and they both have a different constant appearing, these constants still appear here. But now they appear as a quotient. And now, a priori, let's say, a priori, this could be anything, but now it turns out this is always one. Maybe it helps also to compare this situation to electrodynamics. Let's suppose I would do the same thing with electrodynamics. And maybe I can do it with another color. So let's suppose I put, instead of the gravitational force, I put the Coulomb force. Then I would have something like, let's just suppose I have one other particle. I have a particle x1, which is also charged. And let's suppose the particle, so the particle I'm considering on which I execute the force or on which I measure the force is a particle with charge q0. And let's suppose I have another particle which generates an electric field. Then I would find, I would have this law here. Actually, it would have a minus sign, so maybe I should write it like that. X0 minus xj, x1, in this case, divided by x1 minus x0. So that's the Coulomb law. Like it has a very similar form to the gravitational law, but the difference is what is here, m0 is now q0. Now I could do the same as I did before. I could now say, if I'm just interested in the acceleration of this test particle with charge q0, I just combine the two equations. So I divide everything by m inertial, and what I get is I still get the q1, and then I get a factor, namely q0. I just arrange it like that, divided by m inertial, and then I still have this quotient, this law that tells me how the force decreases. So that would be the same thing if I do everything for electrodynamics except instead of for gravity. So now what okay, here should be an equality sign. So now what I found is I have an expression for the acceleration, and the acceleration determines the trajectory. But now I would see that the trajectory depends obviously on how far the other bodies are away, so this x1 and so on. But in particular, it also depends on this quotient. So if I change the structure of my particle, for example, I charge it more, then it has a different acceleration. So for Coulomb's law, the equivalence principle wouldn't hold, because now the trajectory, which is determined by this, really depends on the structure. This is somehow the structure. It's how much charge I have per mass. And the equivalence principle really tells me for gravitation, this is not the case. I don't have such a structure constant. So I guess, I hope this comparison to electrodynamics helps, because there are clearly very different quantities. And you could then just ask, why are they not different also for gravity? And the reason why they're not different is really the equivalence principle tells us they are not different, but we don't really know for sure, so we need to test it experimentally.
Okay, thanks.
Okay, you're welcome. Okay, I think then it's already time to continue on. There is, I mean, of course, I'm still taking questions, but I will then continue with the rest of the actual course. Are there still questions? What I said before. Okay, if not, then we can now really move to, let's say, the part which goes beyond Newtonian gravity, which is an extension of the principle. This is called Einstein equivalence. So what is Einstein equivalence? Einstein essentially postulated that still the weak equivalence should hold. So it includes weak equivalence. But it also contains an additional part. So this plus means I have some additional thing. And this additional statement is the following. The additional statement is that the outcome of any local experiment, so let me write it because it's so important, I want to really write it fully, of any local, and there is some other term which I will maybe discuss later, but you don't need to worry too much about it, non-gravitational experiment in a free-falling laboratory is independent of the velocity and position of the laboratory. Location or position and velocity of the laboratory in space-time. So in space-time means it's also irrelevant when I do the experiment. It will not come out differently if I do something later or earlier. Okay, so what does this tell us? So first of all, this sounds quite easy. It's just a sentence which says, I mean, it's maybe a similarly easy sentence as the famous statement or postulate that the velocity of light is constant. And this is something you can just say in with a few words, but the implications are enormous. Here we have a similar principle. It's quite easy to understand what it means. You just take a lab. I mean, usually this is depicted as a spaceship, but maybe it's actually better to just think of an elevator where the rope is cut, and so you fall freely down because, okay, I don't know whether this is easy, but it's maybe more likely that this happens than that you're in a spaceship. So you can maybe imagine what happens if you're in an elevator that falls down. And now if you think you are doing a physics experiment while you're falling down, then the statement is this physics experiment, the outcome of that experiment will not depend on essentially where this elevator is and what velocity it has. It's just essentially independent of anything around. So this also means that, let's say, if this elevator was now not on Earth, but somewhere else and free falling, in which case it may stay, like you're on the satellite or even far out in space, what you would do in this elevator experimentally would still lead to the same outcome, which means that if this elevator would be closed, so it has no windows and no connection to the outside, you would not be able to see a difference on whether you are now in this falling elevator on Earth, of course, before it hits the ground, or whether you are far away, let's say from gravitational sources, somewhere far out in space and just free falling there. There would be no difference between the two situations. Now, by the way, the fact that it here talks about non-gravitational experiment, I think we will come back to that later, but if you didn't have that, it would be even harder to say what it means, because if you are free falling and doing an experiment again involving gravity inside, so if you have two large masses, for example, inside and try to see how they attract each other, then maybe you're in a more difficult situation, because now free falling within the lab would again be something different from the lab itself. So you should just think of, you have this free-falling lab, and within the lab you do an experiment which does not itself involve gravity. For example, you just do an experiment with light, or something with electromagnetic forces, or weak forces, or strong forces, but not something where you create your own gravitational fields within the lab. Of course, this is always an idealization, and they would anyway be small. But the principle just says something about this non-idealization. The term local also means that this lab has to be very small compared to how the gravitational field, if you want, changes outside. So if, for example, you're doing that on Earth, and if the lab was as big as Earth, this will not count as local, because then within the lab you would have, so to speak, different force vectors. So you would feel tidal forces. Tidal forces are forces by a gravitational field which point in different directions, which, for example, squeeze you or tear you apart. So maybe the picture you should have in mind is that if this is Earth, and you're doing an experiment, of course, if the lab is that big, then you have here a force in this direction, here in this, so you feel that the two forces squeeze you. But of course, if you do an experiment in a tiny lab, I mean tiny in a normal spaceship, which is tiny compared to Earth, then all the forces are, so to speak, intuitively going in the same direction. And local means that you're talking about such a situation. Yeah. The lab is very small compared to the changes in the gravitational field. Okay, so that's what this principle, first of all, says. Now, the question is now, what does it actually imply? And here it now becomes, for the first time, a bit more interesting. Because, maybe you know these nice thought experiments one can do when one assumes that the speed of light is constant, and then from assuming that the speed of light is constant, and the relativity principle, which says that physics is the same in all inertial labs. You can already derive that there must be time dilation. So from two very simple principles, you get a very deep insight, namely that time is not constant. And we can do something similar here. So here, by the way, the principle is different from the relativity principle. It's not talking about inertial frames. So an inertial frame or an inertial coordinate system or an inertial laboratory would be one which, with respect to another laboratory, is in constant velocity. Now, if you talk about the freely falling elevator, then this freely falling elevator is not an inertial system, because it doesn't compare to the Earth, because it's not moving with constant velocity compared to the Earth. So this is really a different principle, but as I said, the principle has equally deep consequences. And maybe if you think back at the time before relativity was developed, you may have at that time, if you lived there, asked the question, what does gravitation do to light? Of course, you have maybe Newton's law. And Newton's law tells you that gravity, and Newton's law is what I wrote down before, that's this law here. It tells you that the force executed on a massive particle of mass m0 obeys this law, so it decreases, for example, like the square. But now light doesn't have a mass. So what happens if a light ray is close to Earth? Is it actually deflected by Earth or not? Newton's law will not give you the answer, simply because this thing here is zero in that case. So maybe an obvious answer you could think would be that the force is just zero that is executed on light, because light doesn't have a mass, therefore light is not affected by gravity. And I don't know what people thought at that time, but I could well imagine that before Einstein came up with these principles and these derivations, that many physicists would have thought that light just goes straight independently of gravitational forces that are around. Now the point is that this answer would contradict this Einstein relativity principle, or in other words, the Einstein equivalence principle. Or in other words, Einstein equivalence principles or Einstein's equivalence principle implies that light will be deflected. And later we will also look at that, of course. I mean, we will come back to that later once we have developed all the mathematical tools, and then we can really calculate gravitational lensing, which is essentially that effect that light, for example, that passes through a heavy mass. Now we may even talk about black holes, is bent when it passes it, and we can get quantitative results about that. But we can already, just from the principle itself, without having developed more, get at least the right orders of magnitude. Not actually a precise result, but essentially qualitatively the correct answer. So let me do that. And that will be maybe the main thing I would like to show you now today, which just essentially should also serve as an illustration of what this principle does. So I see this just as an example. And so in this example, I will also use some notation that is going to be useful later, and that I'm just using already now to make you familiar with it. So first of all, whenever we are talking about, I mean, in relativity theory, and in particular also now in general relativity, we will often look at things from different observers' perspective, if you like. And an observer, for the purpose of relativity, this is not true in quantum mechanics, but for the purpose of relativity, is essentially associated to a coordinate system that I choose. I will come to that, back to that later, but for the moment you may just think of an Earth coordinate system. I'm going to put it in a different color. So you may say there is Earth, and on Earth we have a coordinate system. This is, for example, a coordinate system I could put in my office. There is a horizontal coordinate. And now, for reasons that will become clear very soon in the mathematical part, I will denote one coordinate by x1 with a superscript 1. This just doesn't mean x to the power of 1. It means the first component of the vector x, and then the second component of the vector x is x2. So again, it is not x squared. It's just the second component of a vector x, or it's the component, it's in this coordinate system of it's the second coordinate, so to speak. So let's suppose this blue coordinate system is somehow attached to the ground of my office, x1 points horizontal and x2 vertical. And let's now suppose I have an elevator actually in the corridor outside, and this elevator, I could imagine it's just a box. And in this box I could attach another coordinate system. And in these coordinates I call the y coordinates. So I have here also a one direction, which is the horizontal direction, and I have a two direction, which I call y2. Now, suppose that this elevator here, this black box, is freely falling in a gravitational field, which should just be, so let's for the moment still assume we are in this Newtonian picture. We have just the acceleration of the Earth, small g, that lets this elevator go downwards. So I could actually say in the coordinates, in the blue coordinates, in the x coordinates, this, let's say, origin of the elevator coordinate system, I could give a name. Let's call it E for elevator. So I call this point here E. That's the point E. It's just the origin of the coordinate system of the elevator. Now, if I write XE, what I mean is the coordinate of the point E in relative to the blue system, to the X coordinate system. So because this elevator is falling freely, I could just say somehow, let's suppose it starts from altitude 0, just for simplicity. So then its coordinate is always negative. So in the picture it's positive, but if it falls down, it will soon become negative. And let's suppose we start at time t0 with the elevator just being on the ground, and then we let it fall. Then of course the x2, so the vertical direction, will move like this. That's the well-known law of how something that falls freely starting from 0 moves. Let's also, for simplicity, say that the x position of the elevator is just at 0. So in the picture, this is not well reflected, but I could move this over. It's just they are aligned, these coordinate systems. So let me maybe do it just to make sure I'm not confused. So this actually the coordinate system on Earth, on my office, would be that one. So it's aligned here, and the green one falls down. Now, okay, that's all very simple, but you will see that very simple considerations will arrive at a very deep conclusion, namely that light is deflected. So don't be worried that I'm, for the moment, just doing very simple calculations. We could now say we can, of course, translate everything that is said with respect to the blue coordinate system and in terms of something that is said in terms of the green coordinate systems, which is a coordinate transformation. And the coordinate transformation will play a huge role later. So we'll talk lots about coordinate transformation. So here the coordinate transformation for the horizontal coordinate is very simple because we just aligned them and the elevator just falls downwards and not sidewards. So the x1 and y1, so the coordinates in the horizontal direction are always the same. So it's almost trivial. Now I could say for the vertical coordinate, if I have something given in terms of the elevator coordinates, which are the y coordinates, so I know what is the vertical position of something. So this is just something, some particle that I have in the elevator. Suppose in the elevator I know it has position horizontal, vertical position y2. What is its position with respect to the x system? It's of course y2 minus the origin of the elevator, which we know was just minus 1/2 gt squared. Okay, so that's just how we transform coordinates. By the way, just for consistency, I could say if I do that in the case, I mean, I could now say, of course, I know that in the y coordinates, the elevator position, the origin of the elevator is always at 0. I mean, that's by definition, because E was defined to be the origin of the elevator coordinate system. If I now insert YE into this coordinate transformation here, so I insert the 0 here, I just get for XE exactly this expression. So this is just consistency check that I could make. Of course, it's all simple, so I don't necessarily need to check the consistency, but it's just maybe good to be sure you're on the right page. Now let's suppose we do a non-gravitational experiment in the elevator. So what could be a non-gravitational experiment that we do in the elevator? One thing we could do is to take a light ray. I mean, I take here at some altitude, let's say here h. This is just some altitude within the elevator. I shoot or I take a laser and emit light in this direction and see where and measure when it hits the wall on the right-hand side. Now, what would I expect? Where does it hit the wall on the right-hand side? Because, so this is now where we have to think about the equivalence principle. Because this elevator is freely falling, and because the equivalence principle, this is now the point where it's really relevant, the equivalence principle, because the equivalence principle now tells us that all freely falling labs, all experiments have the same outcome. I could say, oh, I shouldn't really care about the fact that this elevator is now freely falling close to Earth. I could take this elevator and put it far out in space where there is no gravitational field at all. And then the physics, the experiment should have exactly the same outcome as if I did it here on the Earth in the freely falling elevator. And clearly, if I do the same experiment, namely shoot a beam of light in the horizontal direction somewhere far away from any gravitational field out in space, then I know exactly what happens. The light will just go straight. There's no deflection by gravitation because there simply is no gravitation in outer space. So I know that the altitude where it will hit the right wall will still be h. The light ray just goes straight if I'm far away from any gravitational field. And now the equivalence principle tells me it's the same for this falling elevator on Earth, because it's freely falling. The physics has to be the same. Okay, maybe I stressed that now too much, but this is actually the crux of the argument to say that we know already that in the freely falling thing, the trajectory of the light is clear. So what is the trajectory of the light? Maybe I write L for the light ray. If you like. Maybe you could think of a pulse of light, and it has a certain position that depends on time. So what's the position of the light ray? The vertical position will, the horizontal position will just be, let's say, ct, where t, suppose we emit the light at t equals 0, and c is the velocity of light. So I'll find it at position ct after time t. The vertical position of the light pulse, which is the 2 component, the 2 is the vertical one, will always remain on h. That's what I just said in the y coordinate system. That's important. That's only true in the elevator coordinate system, not on Earth, because Earth, with respect to Earth, this experiment is not, Earth is not part of this laboratory, so I couldn't apply the equivalence principle to the reference system of Earth. Now I can do the coordinate transformation from above applied to L. So I just apply these 2 formulas to that. So in the first case, this is trivial. Of course, the horizontal position will always be ct. And the vertical position, so the 2 component now undergoes this coordinate transformation here, which means I just subtract 1/2 gt squared. So what I get is h minus 1/2 gt squared. And there I already have essentially the solution. So what does it mean? If I'm now going back to the Earth coordinate system, which is the x system, so I draw it here again. So this is x1 and x2, and I now draw what this trajectory tells me. Namely, I go here with ct to the right, and the vertical position changes like that. Then obviously what I have here is that I start with h, and then I go to the right, but then there is this quadratic term kicking in, which makes the altitude a bit smaller. So obviously what I have is something like this. So that's what these 2 formulas tell me. So indeed, in the Earth gravitational system, this light ray is actually bent downwards. So this means that if I have light coming in horizontally, close to, let's say, the Earth surface, so I would imagine there's now from my window, which is here on the left, by the way, light coming in horizontally, it will, due to the gravitational field of Earth, be slightly bent downwards. And we got this conclusion without invoking anything else except for the fact that we applied the equivalence principle, and we know how light behaves in far away from the gravitational field, namely it just goes straight. That's what we used here to derive this equation. So you see, a very deep conclusion, namely that light is affected by gravity, which wasn't clear a priori, as I pointed out before, follows from this principle. And I hope this illustrates very well the power that this principle has. Actually, we may even get something a bit more quantitative if you like. You could ask yourself, what's the angle of this deflection? So I could here, I take here a tangent. That is not drawn very nicely, but okay, I just take some point. Let's say I say here, I let the light cross a distance of delta x. Let's suppose this elevator or whatever experiment I do lets the light make a path of length delta x. And now after delta x, let's suppose initially it was horizontal, and now I ask myself, what's now the angle phi that it, what's the deflection angle? How much deflection did it get in terms of an angle? Now, what's the deflection angle phi quantitatively? And that's now very easy. This is a simple geometric argument we could use. And I'll do that here because it's actually quite interesting to see that the equivalence principle doesn't only give us purely qualitative results, it also gives us a flavor of a quantitative result, although not an exact one, as I will point out later. So the angle is essentially the derivative of xl to the dx of dlx2 by dlx1. So dlx2 is just how much it goes in the vertical direction, and dlx1 is how much it goes in the horizontal one. Approximately for small angles, this is just the expression for the angle. Of course, I could put the sign to make it precise, but the sign of a small angle is just linear in the angle approximately. So that's the formula, and I want to evaluate this derivative at the point delta x, so to speak. So what's, yes?
There are some questions, maybe that might be of interest. Like one question is asking now if the light is deflecting like this, whether now the velocity of light, like the velocity of the light is exceeding the light velocity.
Oh, yes, that's a very good question. Actually, this question is something that I will have to come back to a bit later. So I was just saying that this equivalence principle gives us a very good answer, but not a precise one. And this has exactly also to do with this type of question, because the argument I'm now making doesn't take into account essentially, so far I haven't actually used special relativity. So I haven't used the fact that, or I haven't used any knowledge we have about space-time in special relativity. I just started from a completely classical picture, essentially from a Newtonian picture, and got this deviation. Now, indeed, it would be the case that if I just make this argument now in that way, in this Newtonian sense, I would get a slightly larger velocity than the velocity of light. And of course, the resolution is then that I also need to impose the relativity principle in the same way as I do, as I invoke the, sorry, not impose, invoke the relativity principle in the same way as I do it when I derive special relativity, and this would lead to the conclusion that the clock that is running, let's say here, or the clock that is running here will run at a different speed. So therefore, actually, the velocity of light, if you measure it in terms of a clock, will again be the right one, but we have to take into account that the clock here and the clock here will run different. We haven't done this because here I just wrote t for, so to speak, a global time. So in that sense, this whole derivation is still a very rough approximation, and we have to take into account more later, and we will do so. So this is really just, in a way, an introductory example where we neglect certain aspects of relativity, and the result will indeed, for that reason, be wrong by exactly a factor of 2. And later, once we have learned all the tools of differential geometry, we can return to this example and make it precise. But for that, we need to do a lot of, first learn a lot about geometry, and then we can make that precise. But that's really a very good point that you notice that that's indeed a problem in this simple example. I hope this clarifies the question.
Thanks.
Yes, okay. So let's now just calculate this derivative. So it's essentially what I can do here to calculate this is just to say that dxl1, so an infinite, I mean by dxl1 I mean just a small, at the moment you don't even need to think about the derivative. If you don't want, you can just think of here a small element in this direction and a small one in this direction, and then of course dxl1 is essentially c dt, where dt would be the corresponding short time it takes to travel the distance dxL1. And then if I now insert, so if I replace this, then I indeed get a formula where I have dxL2. Again, this is not a square, remember that. And I take the derivative to ct. Now dxL2 we have here, this is just minus 1/2 gt squared. So if I now take the derivative to cbt, I get rid, this is really, okay, that's a bit unfortunate, but this is really a square, because t is just a scalar. This will later not be a problem in the notation, because we will very rarely have squares of vectors. So whenever you have a vector like x and the 2, then it's usually just an index. So what we get here is just, I take the derivative of this to the c and take into account the fact that I also have here a c factor, so I get an additional 1 over c. So what I get is minus gt divided by c. And now I also can use the fact that if I'm now evaluating that, I want to evaluate that at the time t, when the ray is here. So I insert for t essentially expression delta x divided by c, because that's exactly the time I have, again ignoring special relativistic effect when the light pulses here. So I just insert this time, and so what I get is here minus g over c squared times delta x. So that's the formula for how much the light is deflected. So what does it tell us? It tells us that if I have now an incoming light ray from here, and now I look and I observe it over a distance of delta x, so that's delta x, and I ask myself how much angle did it acquire while traveling this distance delta x, then the answer is that it's proportional to delta x, and proportionality factor is g divided by c squared. So actually, you may wonder what number that is, and you can, of course, easily calculate it. G is roughly 10. By the way, the units are also right. If you can easily check that this is actually a unit of 1 over meter. And if you insert numbers, you get something, I think, of the order of 1 light year. It's not precise, but it's surprisingly roughly 1 light year. Of course, it's an inverse to the -1. So in other words, the angle corresponds to essentially delta x measured in terms of light years. So I just take this short distance. It's of course very small a very small number if I measure this distance between my two hands in terms of light years. This very small number will be actually a number, it's probably 10 to the -15 if I take here a meter roughly, or something of that order. So it's 10 to the -15. So the angle acquired by the light while traveling this distance will be of the order of 10 to the -15. So that's the result we get. And now it turns out, as I now said several times, these are approximations because we neglected certain effects. And we will later, of course, understand what these effects are that we neglected. But one will be able to prove that the correct formula for this angle looks almost exactly like this, with the only difference that there is a factor 2 here in front. So it's twice as much. So essentially, interestingly, the effect that we had just takes into account one thing, and if I consider the fact that, if I consider full relativity, not only the principle, but everything that follows from it, including the fact that the speed of light is constant and so on, I get here exactly this formula with a factor of 2. So we almost, in that sense, got the right result just from this principle. Okay, so that was, and I think I made this clear, not supposed to be a precise calculation. It was more something to illustrate to you where this is going and what relativity does. This was probably really the way, I guess, Einstein thought about it before he had the theory. He probably had these thought experiments with elevators and so on, and he thought about what would happen if a light ray passes the Earth and could make these statements. Now, if we,
I have one question.
yes.
Could you maybe clarify a little bit more what in the equivalence principle, what you mean by non-gravitational experiment? And
Oh, yes. So what I mean, yes, that's a good question as well. And that's actually something that also distinguishes, for example, the Einstein equivalence from other versions. For example, one may phrase a strong equivalence principle, with the difference that you actually omit this conditioning and you just say for any local experiment. So this just makes the equivalence principle in a way a bit weaker. So you see, you could generally what you should do is to say that the weaker the principle is based on which you can derive a theory, the better this is. So you want to have as weak as possible principle. Now, by excluding gravitational experiments, what was meant is that now we did really a non-gravitational experiment in the sense that this experiment, if we did it far out in space, not close to Earth, and so the experiment was now just send a beam of light in the horizontal direction. This experiment has nothing to do with gravity. We can essentially see what the result is of this experiment without invoking gravity. Of course, we could have done another experiment. For example, we could have taken two heavy masses into this lab and measured how far, what's the force between these two masses. Now, Einstein's version of the equivalence principle would not tell us anything about such an experiment. Simply, it wouldn't say it's wrong to assume that it's the same here in an elevator or far out in space, but it simply doesn't make a statement about it. And I think this is, in a way, making, of course, it makes the principle weaker because the principle now talks about fewer things, but it's also avoiding a few things that would not be well defined, because what this local means is essentially that you're in a small enough lab so that the gravitational field is essentially constant throughout the lab. And so if you now had in this local lab itself, again, a mass that creates a gravitational field that is relevant, then you would kind of contradict this locality, because now it's no longer, the lab is now no longer small enough. You can no longer argue that the lab is smaller than the changes in the gravitational field. So by excluding gravitational experiments from the principle, you make this in a way a bit cleaner. That's one way to see it. But what it means is just, you should have an experiment where if you're far out in space, you don't need gravity to evaluate what the outcome is. And this was certainly the case for this light ray experiment, where we just say light just moves straight and this has nothing to do with gravity. Okay, I hope this clarified the question. Let me now use the last few minutes to say something about what this all now will lead to, or what we can learn from this. So we have now somehow seen that in this derivation, if you think back, what did we do in this derivation? We essentially really did it in a geometric way, in the following sense. So what we said, we looked at this situation and we just looked at the same situation from the point of view of two coordinate systems. And we went to one coordinate system, namely that of the free-falling elevator, in which the gravitational field is just transformed away. So the equivalence principle, of course, was useful then to say that we could then do the same away from the gravitational field, but essentially we could reduce the problem to so we went into a coordinate system, we transformed our problem into a coordinate system in which gravitational effects are absent, namely the coordinate system of the elevator. Now you could ask whether this is something you can do in general. So you could ask yourself, wherever you are, could you always go into a coordinate system in which gravitation is no longer present? And the answer is locally, you can always do it. You just take a free-falling lab wherever you are. So you can even go close to a black hole and just enclose yourself into a free-falling lab. And within that lab, everything will be as if there was no gravitational force. And what this means is really geometrically or mathematically went into you solve your problem now in a coordinate system, like in the coordinate system of the lab, in which no gravitation has to be taken into account. So by a clever choice of the coordinate system, you can somehow get rid of gravity. Now, of course, you can do that locally everywhere. Actually, in this particular experiment, you could say in this particular situation close to Earth, you could say this coordinate system, the y coordinate system, the blue one that the green one that I introduced is a coordinate system in which there is no gravity. And you can solve all problems as if there was no gravity. You just have to work in that coordinate system. And this coordinate system would even be globally defined everywhere on the surface of Earth. However, if you are in a situation like this one, where you have Earth somewhere and you have locations here and here, you could still ask, is there a coordinate system where at the same time gravitational effects disappear here and here? But this will not exist. So you will not find a coordinate system in which you can at the same time get rid of gravitation here and here. So you can find a coordinate system according to which there is no gravitation when you're here, and you can find out one where there is no gravitation here, but you cannot find a coordinate system where simultaneously there is no gravitation here and here. So that's a bit a shame, because if we could find a coordinate system in which we get rid of gravity completely, we could say that gravity is really something purely geometrical, in the sense that with a clever choice of coordinate system, so I mean, change of coordinate system is a geometric notion, and it will mean that by just a change of coordinates, we got rid of that force completely. And that would be nice, because this would, of course, simplify things if we could see gravity just as something that goes away by changes of coordinates. Now, the insight of general relativity is that we can still somehow do this almost, so we cannot get really rid of gravity, but we can always we can still translate gravity into a purely geometric notion. But for that, we have to assume that space-time is curved. So in other words, what Einstein or what general relativity at the end will teach us is that this principle we apply to solve this problem, this very simple problem here, even applies in the general case. We can always somehow think of a situation where the gravity is not a force, but there's just geometry and we work in the right coordinate systems. And there's not a force field. We're just changing coordinates, and in the right coordinate systems we are fine. So gravity can be turned into something purely geometric. And that's what general relativity really does. It essentially says all of gravity can be captured by the right geometry, but this geometry will be a geometry in which space and time are curved. And that leads me to the, okay, I still have maybe 1 minute, to the final thing I wanted to do today, namely to give you an outlook on where we will go in this course. And of course, one of the central elements of general relativity are the Einstein equations. The Einstein equations, it's actually a set of equations, but it can be written as one equation with indices mu and nu. So mu and nu will be indices that go from 0 to 3. This is 4 dimensions, and it looks like this. So it's actually a very simple thing. It's just an equation that I can write down essentially on one line, even with a very big font that I'm using here. It's this equation. Now, as I said at the beginning, you will not understand this equation now, probably, but the goal of the lecture is that you will understand all these objects. But let me nevertheless say a few things about them. This G, which has a name, it's called the Einstein Tensor, is essentially a quantification of a purely geometric, is something purely geometric. It's essentially telling us how curved is space-time. This other term, this is the so-called cosmological constant. And for the moment, we can talk, I mean, even in certain formulations, initial formulations, this wasn't even there. Let's just not think about it. I just wrote it for completeness, and we will talk about it. But for the point I want to make, it's not relevant at this point. You can also assume that this is actually a small term for certain purposes. But the right-hand side is again important. This is the so-called stress energy tensor. And this characterizes essentially the matter. So this characterizes the stuff that is in the universe. Light, light and particles and so on. Everything that is actually in the universe is captured by this thing. Now the Einstein equation essentially tells us that the geometry of space-time can be chosen by the equality in a way, or if the geometry is chosen depending on how the matter is distributed in space-time. By the way, this proportionality constant is the gravitational constant, and this is just the velocity of light. Then all of gravity is captured by this geometry. So in other words, if we choose the geometry of space-time in a particular way, so if we curve it in the right way, and how we have to curve it is given by how the matter is distributed in space-time, then there is no gravitational force. It's just the geometry that captures everything. In the very same way as in this elevator example, where everything is just captured by going to the right coordinate system. We didn't have a force field at the end. We never talked about the force in this example. We just solved it geometrically. And I hope the example makes clear what is meant by solving something geometrically. And that is really what general relativity achieves. So it essentially lets gravity as a force disappear. So in general relativity, gravity force doesn't exist any longer. It's all captured by the geometry of space-time. Now, of course, in order to understand this equality, we need to understand the notion of how do you characterize curvature of a four-dimensional object, space-time, mathematically. So we will need quite some effort to actually be able to understand what this G means. This will take us several weeks. Then we will also, in a second part, spend some time trying to achieve an understanding of how we characterize a matter distribution in this curved space-time. But once we have that, we can understand that. At this point, you should just understand the Einstein equations is a relation between the geometry of space-time and the matter distribution. Once we have an understanding of this and this, which will take us almost 2/3 of the semester, we will have 1/3 of the semester left to try to see what implications this has. And this is then the really interesting part, because there we will see all these things that you probably have heard about, like black holes, gravitational waves, and so on. These are all phenomena that we can understand once we understand these equations. Okay, I think that's all that I wanted to tell you today. So just to briefly review, so what I told you today is, first of all, where does GR lie in the landscape of physics? And essentially the answer is it's there where gravity plays a role, but quantum mechanics is not there, unfortunately, one should say. Then I told you what principle it is based on, and one of the main principles that directed the development of relativity is this equivalence principle that I explained. Then we saw the power of this principle in an example, namely the principle allows us to understand how light bends, and you could also see in this example what it means to have a geometric understanding of a force, because in this example gravity was really not a force. It just solved, if you can go back to it and you will never see a force vector that we wrote down. We just solved it geometrically. And then now finally I told you that what Einstein achieved with the general relativity is to make this a general thing, namely that we can get rid of gravity as a force and just include it into the geometry of space-time. And how this geometry has to look like is determined by this equation, which relates geometry to the distribution of matter in the universe. So next time we will have to start with the hard work. We will have to do a lot of differential geometry to understand this notion. And to do that, I will at the very beginning just introduce some notation that will be useful. So I will say a few things about that you're certainly familiar with about vector spaces and linear maps, but I need to introduce them in a way that allows me to introduce the notation we are going to use. So next Thursday will probably be quite easy to follow, but maybe slightly boring because you may know these concepts, but it's necessary just that to have a common language, essentially. We need, first of all, a common language to talk about relativity. And then the next few weeks we will talk about this, or talk about differential geometry. And the goal of talking about differential geometry is to finally understand what this object means. Okay, that's was it for today. I'm very glad most of you seem to have stayed until the end. I hope you will return on Thursday. And as I said, if you want to decide whether you stay in the lecture, maybe you should wait for the Thursday lecture because it will give you a better impression on what technical level we will work on at the end. But I hope this will be feasible for most of you. Okay, thanks a lot. And of course, I'll stay around for a bit to take questions if there are any. And for those who leave now, see you on Thursday.